I know this section actually ended up being a lot, and this is, trust me, this is the last little piece that we're going to need to cover, but it is still very important. So this is actually just the entirety of this section. The reason why we did everything that we did beforehand was to get to this point in time. So this is simplifying. Simplifying. This is why I became a math teacher. Radical expressions. Radical expressions, the title of this whole chapter. So let's work with them. Let's get some complicated examples going. First things first, radical expressions actually tend to be a little more strict when you're trying to simplify them. So rads are strict. These are a little more complicated, but it doesn't mean we still can't work with them. So I'm going to start off with a pretty easy example. Let's say I've got something like the square root of 360 times x squared times y. The goal of simplifying radicals is look at what my index is. So in this case, there's an implied 2 here. This means that I want pairs. And you'll kind of see what I mean by that in a little bit. So I want pairs. Why? Because 2 corresponds to pairs. Okay. I want to pull anything out that I can get a pair of. Well, right now I can see a couple pairs already. I've got a 2 right here, and I'm looking to see if I can make a pair in here somehow, but we'll get to that in a second. First things first, look for something that I can take the perfect square of, which is the same thing as looking for a pair. 360 is not a nice number to take the square root of. I can't pull out a perfect square from it at first glance. What I can do is 360, you can probably agree with me, is the same thing as 36 times 10. 36 we may recognize as being a perfect square. This is 6 squared. Okay. I'm going to use that idea, and I'm just going to replace that. So I've got the square root of 360x squared y. This is the same thing as the square root of 6 squared times 10 times x squared times y. I just broke 360 up into 6 squared times 10. I left everything else the same. This next part is very important, and it helps us with everything else that we're going to do for our assignment and for later dates. You'll see what I mean later. My process is take everything that's a pair and put it next to each other inside its own radical. A property says if you take a bunch of things and multiply them together, you can break them up into individual radicals, and that's what I'm going to do. Take all of your pairs and put them in their own radical. So what's that going to compose of? I've got a pair right here and a pair right there. I'm going to get a square root going. I've got my 6 pair, and I have my x pair. And then I'm going to have the other stuff in its own radical. Now what I can do is, hey, I'm taking the square root of a pair and a square root of another pair. That's just going to be one of each. Okay? So you can think about this too as you're taking this power and you're dividing it by whatever number is on the outside, your index. That's going to give me 6 times x. And the remainder, I can't pull out a square from, so that is as simplified as I can get. So that's a relatively easy example. I'm going to go ahead and erase everything. The important concept behind that is the index determines what I pull out. Okay? Index determines what I pull out. The index was 2, so I pulled out pairs. If the index is 5, I pull out powers of 5. Okay? And we'll see that in another example. So for this last one, I've got something a little more complicated. Let's say I've got something like the cubed root of 270 x to the 5th y to the 7th. Okay? I picked easy numbers for us to work with. So since my index is 3, I'm looking for multiples of 3 to pull out. Okay? Well, 270, I'm going to do kind of a similar trick. 270, I know is the same thing as 27 times 10. And this so happens to be a multiple of 3 for its power. 3 times 3 times 3 gives us 27. I'm going to use that and I'm going to substitute it in. So I've got the cubed root of 270 x to the 5th y to the 7th is the same thing as the cubed root of 3 cubed times 10 times x to the 5th times y to the 7th. Are there any other triples that I can pull out of this to put by themselves? It may not seem like it at first because 5 and 7 don't divide by 3, but properties of exponents act a little weird. Instead of dividing and multiplying, they add and subtract. What I'm going to do is I can break up x to the 5th and y to the 7th into x to the 3rd, x squared, and y to the 6th, y to the 1st. I'm multiplying those, so I add the powers. So 6 plus 1 is 7, and 3 plus 2 is 5. That's perfectly fine. So I'm going to take that, I'm going to rewrite it as this long thing. It looks long and complicated, but I think this is an easier way of understanding what we're doing. 3 to the 3rd is fine. 10 can't go any further. X to the 5th, I said we're going to make it x cubed, x squared. And y to the 7th, I said we're going to make it y to the 6th, y to the 1st. The way I like to do it is I take all of my multiples of 3, put it in one thing, and the rest goes in another. This is the same thing as the cubed root of my triples, which is going to be 3 cubed, x cubed, y to the 6th, and then a cubed root of the rest of it. X squared, y to the 1st. If I take the cubed root of everything over here, I'm dividing the powers by 3. This is the same thing as 3 to the 3rd over 3, which is 3. X cubed, the cubed root of that is x. Y to the 6th, the cubed root of that is y squared. And then since none of the other stuff has a triple in it, I leave it the same. That's my simplified result. So yes, radicals are a little more difficult to deal with. I think they're kind of fun, though, once you get the hang of it and do a little bit more practice with it. This piece took me forever to grasp when I was in Algebra 2. So this isn't very, very simple to get the first try. If you do it, fantastic. If not, it just requires a little more practice.